We're picking up here on chapter 5. So back forward to chapter 5, which should be the last chapter that'll be up on our upcoming exam here on Monday coming up. So in this chapter, we're going to talk about grams, moles, molar mass. We're also going to talk about empirical formulas, molecular formulas, how to officially sort of calculate all those things. So let us get into it here. So the first thing we're going to talk about is atomic mass. And remember that the atomic mass is actually what we do find on the periodic table, not that mass number, but it is the number that we do see here on the bottom. And that is the atomic mass of a particular element. It is obviously related to the number of protons, electrons, and neutrons that there are within the atom. But obviously, atoms, as we talked about in a previous chapter, are extremely small. So you can't really like pick one up and put it on a scale or anything like that. So usually in science or chemistry or things like that, where we can't sort of directly measure something, what we oftentimes will do is sort of pick something and use that as a standard and compare basically everybody else to it. And that's essentially what was done with the atomic mass. An isotope of carbon was chosen as sort of the standard to compare everybody to and sort of figure out the atomic masses of everybody. And that was the carbon-12 isotope. And the carbon-12 isotope has exactly 6 protons and 6 neutrons and has a mass of what is sometimes referred to as 12 AMU, or atomic mass units. Not too many people call it Daltons, or come across it all that often, but an atomic mass unit is also sometimes referred to as a Dalton as well. And they sort of assigned the carbon-12 isotope as sort of the standard to figure out the atomic masses of everybody else that we sort of see on the periodic table. Basically what they kind of did is just kind of said, hey, this guy's only like 1% as big as the carbon-12 isotope, and they do some math to sort of figure it out. So 1 AMU is basically 1/12 the mass of a carbon-12 isotope. So for example, like I said, experiments have shown that on average, a hydrogen atom is only about 8.4% as massive as a carbon-12 isotope. So if you kind of do the math on that, take 8.4%, kind of convert it into a decimal, which is what we see here, and times it by 12, we get something like 1.008, which is sort of the number that we do see on the bottom there of the periodic table underneath hydrogen. Similar calculations have been done for things like oxygen and iron, which is 16 and 5585. When we do sort of take that number off the periodic table, there are a couple of different versions of sort of how we use that number. One of which we don't use it all that much is we can take that number off, and that would give you basically how many AMU there are in an atom. So that's one very common sort of use of that. Later, we'll talk about molar mass, which is also taking that number off the bottom of the table, and that gives you how many grams per mole. These guys, as we'll talk about in a sec, are essentially equivalent to each other in terms of their value or number that you get. But most of the time, we will take it usually in grams per mole, but you can use it as AMU per atom when you do pull it off. Also, typically speaking, 4 sig figs is usually what you pull off for that number. Again, depending on your periodic table, may have a lot of numbers, may have a little less numbers, but 4 significant figures is typically what we do sort of pull off of the periodic table to use in calculations. Any questions on that there? Now, if we look at something like carbon, though, on the periodic table, we do see that for carbon, it does say 12.01, which if the carbon-12 isotope is the standard and has a mass of 12, how come it kind of says 12.01? And that is because what we actually see on the periodic table underneath the symbols are really average atomic masses, even though most people don't call it average atomic masses or anything like that. But they are actually average atomic masses of all the naturally occurring isotopes for that particular element. So for all the naturally occurring isotopes for that particular element, that is really the number that we get there. So for example, something like carbon, maybe carbon 12, carbon 13 is used to get to that 12.0 number as well. There actually is a formula that we could use to actually calculate the atomic mass or average atomic mass. And basically, we could take the percent abundance, our relative abundance, that's basically the percentage at which a particular isotope occurs, times the atomic mass of the first isotope, then added to the percentage times the atomic mass of the second isotope. And depending on how many isotopes you have, you just sort of continue that pattern. Obviously, if you get 100%, then that should be all the naturally occurring isotopes that are present. You know, if you don't have all the percentages given to you, you could assume 100% and figure out the missing percentage and stuff like that. So a lot of times it's sometimes referred to as relative abundance, percent relative abundance, or something like that. And this, again, is the percentage at which that isotope occurs naturally versus obviously the other isotopes that are there. If you do use this formula, a couple of things, just mathematically wise, we do want to convert our percentage into a decimal, so you can move the decimal place a couple places to the left there, or divide by 100 to do so. And it is actually plus here in between both of those calculations and not multiplying. People always want to multiply kind of when they do this one, but you are just sort of adding those together. So by using this sort of formula, that gets us basically the average atomic mass that we sort of see on the periodic table. So if we look at something like perhaps carbon here, so for example, the natural abundance of carbon 12 and carbon 13 is 98.89% carbon 12 and 1.1% carbon 13. And again, if you add these guys together, that's about 100%. So we know we have all of our sort of isotopes present. So we do the calculation we just talked about. This is basically the percentage, which is 98%, converted into a decimal, times the atomic mass of that first isotope, which is the carbon 12 isotope. And we then add it to the percent abundance of the second isotope. So that is 1.1% converted to a decimal times the atomic mass of our second isotope there, which obviously this guy was the carbon 13 isotope. And that gets us our 12.01, like we do see on the periodic table underneath carbon. And again, it's basically an averaging of all the naturally occurring isotopes for that particular element. It is important to know, again, although, you know, most people don't necessarily refer to it as an average atomic mass, you know, if you were to sort of pull out some carbon atoms and able to individually sort of mass them out and stuff like that, you really would never find a carbon atom that has a mass of 12.01. It would either be like the carbon 12 isotope that has a mass of 12 or the carbon 13 isotope that has a mass of 13 and change. So again, what we're looking at is just that average value between them. Any questions on that there? Yeah. We're going to talk about a couple slides in a row. They could do some stuff like mass spec, which we're going to talk about here in just a second, a little bit. And it kind of separates out everything and sort of the percentages that they occur. So atoms have very tiny masses, obviously, and so they create units to avoid very small numbers. So this is the relationship, in case you're ever curious about an atomic mass unit and a gram. So that is the relationship between the two. 1 AMU is equal to 1.66 times 10 to the minus 24 grams. So as we talked about, we can use these, and again, we don't very often in chemistry kind of use AMU and stuff like that, but we still can. So if we had 431 carbon atoms, we could go to the periodic table, and once again, using that number as basically 12.01 AMU per atom. And you can use it like a conversion factor like that. You could also flip it around and have obviously an atom up on top, which would be 12.01 AMU. So here we're going to take our 431 carbon atoms. We're going to multiply it by what we get from the periodic table. Here the atoms do cancel, and it does give us something like 5176 AMU would be that. Obviously, you can use conversion on the other page there to convert it into grams if you would like to. Same thing here, 75 atoms of aluminum. Once again, that 2698 number does come from underneath there on the periodic table. Aluminum, and we could pull it off again as 2698 AMU per atom. R an atom is 26.988 AMU. In this case, we're starting with atoms, so we want atoms on the bottom so that they do cancel. Multiplying across the top gives us 2024 AMU. And again, if we wanted sort of a gram reference for it, we could use that conversion factor there on the other page. Any questions on those calculations there? So to answer sort of the question that was asked a second ago, one way that we could kind of figure out the abundances of these isotopes is through a process known as mass spectrometry, or mass spec is sometimes referred to. And atoms or molecules are basically shot down after they're sort of ionized down a tube. And they're basically sort of fragmented out and broken down during the ionization processes. And based on sort of a magnetic field, they're sort of separated out into basically by size and mass, and sort of the relative peaks that you see give you sort of that percentage of their abundance that is present along the way. And here's sort of a mass spec graph, and this is sort of what comes out. And as you can see, you know, you got based on sort of the peaks that you get and sort of the largeness of the peaks, if you will, that's sort of, you can sort of figure out the percent abundance of the different isotopes that we see, how they separate it by relative masses. Again, obviously the isotopes will have different masses because they do have different numbers of neutrons, so they sort of separate it out by mass. And again, sort of those different size peaks that we see allow us to figure out, you know, this guy's like, you know, 50% this isotope or 70% this isotope along the way. And here's sort of a little diagram of what a mass spec looks like. Again, sample comes in, basically heats it up, ionizes it through here. It actually goes through an electrical field first, and then a magnetic field. And as you can see, it will hit sort of the detection screen where it'll give you those sort of peaks. And again, it sort of separates them out by mass. Heavier particles kind of coming out a little bit later, lighter particles coming out before. And again, based on the sort of peak heights that we see, gives us that percentage that we do see. Question on that there. All right, so why don't we try one? If copper is 69.17% copper 63, and it has a mass of 62.9396 AMU, and the rest is copper 65 with a mass of 64.9278 AMU. Look, so we'd have two isotopes here of not carbon, copper, that would work. So we do want to figure out the atomic mass. So we are going to use that formula that we talked about here a second ago. Basically the percentage of the first isotope times the atomic mass of that first guy, plus the percentage of the second times the atomic mass of the second, and so forth. So in this case, we know that there are 69.17% of it is the copper 63 that has a mass of 62.9396 AMU. We know the rest of it is copper 65 that has a mass of 64.9278. So to use this, we obviously need the percentage of both of them. We are not given the second percentage, but we do know obviously that is said that that is all the different isotopes that we have. So we can assume 100% would give us 100% of all the isotopes, subtracting the 69.17%, that is the copper 63 isotope, would give us 3083 here as our missing percentage here for our second isotope. So now we have obviously the percentages of each of them. We could go into our formula. So our atomic mass would equal the percentage of our first isotope. Again, we do need to convert it into a decimal. So I'm just going to move it over a couple places there to the left. And we're going to times it by the mass of the first element. And again, here we're actually going to add it, not multiply, but add it to the percentage of the second one. And again, if you don't want to move to decimal, you can just divide it by 100. It will do it for you. And times it by 64.9278 AMU. And that will get us there. $63.55 AMU, which if you look on the periodic table underneath copper, that is about what you see there as well. Question on how to calculate atomic mass there from isotopes. To get variations of this, obviously, like we just did here, you might have to figure out a missing percentage if you're not given all the percentages. You may just be given the atomic mass or have the atomic mass for the periodic table, and maybe you need to figure out a percentage of an isotope or the mass of a specific isotope. So again, those are some variations on this type of problem. Any questions on atomic mass or how to calculate it? Yeah. There it is. Hopefully they agree with us. I hope they do, so that's good. All right, so the next thing we're going to talk about is really conversions between grams, moles, and all that kind of stuff. So the first thing we're going to talk about is moles. And the mole, this is the abbreviation for a mole, which is MOL. They had to take something off, so they took the E off. So it's really important when you do see the MOL abbreviation that you do understand that it is moles. It's very commonly misunderstood as being molecules. So sometimes people see that MOL and they automatically kind of think molecules, but it is definitely moles. For the most part, if they want molecules, they will write out molecules in problems and stuff like that. So again, if you see that, it is not a shorthand for molecules, but it is moles. A mole basically is the amount of substances that we see in basically 12 grams of the carbon-12 isotope. And a mole is represented by basically Avogadro's number. So in life, we have a lot of words that represent a certain amount of something, right? When we say we have a dozen roses, that's 12 roses usually. We got a pair of something that usually represents 2. They don't use it all that much anymore. If you have a gross of something, that's like 144. So when we say certain words, it does represent a certain amount of a certain substance. And that's the same thing when we do say a mole. It represents basically Avogadro's numbers worth of something. And that is the number on the bottom there, which is usually sort of rounded there to 6.022 times 10 to the 23. And that, again, is Avogadro's number. Now, when we use this, the units that go with Avogadro's number, frankly, can be anything you want. So a lot of times we use them as atoms. They could be molecules if we're dealing with molecules. They could be particles, you know, they could be shoes or, you know, pizzas, whatever it may be, hot dogs, since it was 4th of July, all that good stuff. So we do see a wide variety of units that could be associated with Avogadro's number. Obviously, in chemistry, atoms and molecules are very popular 2 units that we do use with that number. It really doesn't matter the unit, the number stays the same. So it kind of all works the same. It's just sort of that unit part that's a little bit different. We use Avogadro's number as really a conversion factor to go from really 2 ways, either going from moles to atoms or molecules, or obviously the opposite way there, atoms or molecules back to moles. Should you use Avogadro's number in every situation? The answer is no. And sometimes people want to use it in every situation because they're like, I learned that number. It seems like a good idea. Let's just throw it into every calculation that we ever do. So really, Avogadro's number should really only be used in a situation where, frankly, either you are looking for atoms or molecules as like an answer or something like that, or you're given something in atoms and molecules. Other than that, if there's really no mention of atoms, molecules, or anything like that, you don't need to use Avogadro's number But again, a lot of times people try to use it a lot. So we can use Avogadro's number really as a conversion factor. So you can put it up on top, 6.022 times 10 to the 23, again, atoms or molecules over a mole. Or you could do the opposite there, a mole up on top, and obviously divide by Avogadro's number by putting it at the bottom there. Another sort of really important conversion factor, and probably one that we use more even than using Avogadro's number, is actually using molar mass. So molar mass is a conversion factor that we use a lot in chemistry. So let's talk a little bit about molar mass. Molar mass is the mass of whatever it may be, 1 mole of any type of substance in grams. And we get the molar mass from the exact same spot as we get the atomic mass for. So you can take any element you like from the periodic table there, and as we just used it as 1.008 AMU per atom, that is equivalent as saying there is 1.008 grams per mole. So this is what is referred to as the molar mass. Basically how many grams there are per mole. The number that we see on the periodic table is always the grams part, and it's always 1 mole. So we always use 1 mole and how many grams that we have there. Once again, much like atomic mass here, we go for sig figs when we pull that off the periodic table is traditionally what we want to use it for. Again, numerically equal to each other, the AMU per atom and the grams per mole are numerically basically equal to each other if you go through the conversion factor. Molar mass is definitely the one we use the most, and is the one that we use to go from grams to moles, or obviously backwards, moles back to grams. And once again, we'd use it as a conversion factor as grams up on top, and moles are moles and grams. Now, once again, whenever you are calculating the molar mass of something, it is based on just the formula. So what I mean by that is, for example, we could do it for obviously what we have here, something like hydrogen. If we had something like water, for example, H2O, we could figure out the molar mass of something like water. It would be 2 times the molar mass of hydrogen from the periodic table, plus the molar mass of oxygen from the periodic table. And that is going to give us our molar mass here of water of 18.02 grams per mole. Once again, the grams stays with the 18.02, and it is per 1 mole. Now, when we have something like water in a equation, and maybe it's got a coefficient in front of it, like a 4, and if we wanted to calculate the molar mass of it, it is still 18.02. So regardless of if it is in a equation or something like that where there's coefficients, if you are asked to calculate the molar mass of something, it is just strictly take the formula, the H2O part in this example, and that is how you should calculate it. You should not use the 4 ever to calculate the molar mass, and that's because, again, it is per mole. So 1 mole would be just the formula in every situation, and that is what you should calculate. Later on, when we talk about stoichiometry, that is where we use those like coefficients and stuff like that, but molar mass is always just per mole. That's also a very common mistake that people kind of do. They kind of try to incorporate especially when they're dealing with equations, that into the molar mass. Questions on that there? So the relationship again between our Avogadro's number and molar mass is something like this. If we have 1.008 grams of hydrogen for every 1 mole of hydrogen, 1 mole of hydrogen would have 6.022 times 10 to the 23 atoms of hydrogen. Again, the relationship there is basically they're the same amount. Just like what we just did there with our water. For every 1 mole water, there would be 18.02 grams of water, would give us 1 mole of the water. And once again here, 1 mole of water would equal 6.022 times 10 to the 23. And this would be molecules here of water, as water is a molecule, not an atom like we have with just hydrogen. So again, if you have atoms, you would be dividing by Avogadro's number. To get to moles. And if you have moles, you would be multiplying by Avogadro's number there to get to atoms or molecules. The moles would cancel, atoms would cancel. And kind of the same thing here. If you had grams, you would divide by the molar mass to get to moles. And if you had moles, you would multiply by the molar mass to get to grams. Once again, on the right here, we will use way more than Avogadro's number there on the left, but Avogadro's number does pop up occasionally along the way. But definitely the conversion from grams to moles or moles to grams is something that we do in a lot of calculations, obviously, here in chemistry. So again, you can relate it to just an individual element. If you have some type of compound or molecule, you basically just add up all the parts, and that gives you how many grams there are per mole. Any questions on that there? So if I had something like 5562 grams of CH4, and I want to know how many moles that was and how many molecules, why don't you give this a go, see what you come up with. From the periodic table, carbon 12.01 and our hydrogen 1.008. Okay, let's take a look. So we're starting with grams. We do want moles. So once again, our conversion to go from grams to moles is the molar mass from the periodic table is where we get that from. We also want to go to molecules as well. So our conversion from moles to molecules is Avogadro's number. So in this case, we will need to use both things that we've been talking about here. So we might as well figure out the molar mass here of our CH4. So that would be 1 carbon at 12.01 from the periodic table, plus there are 4 hydrogens, each at 1.008 grams per mole from the periodic table. That gets us about 1604. And once again, the number goes with the grams, and it is per 1 mole. So we'll start with our 55.62 grams of CH4. I'm going to approach this like dimensional analysis. So frankly, I got grams up on top, so I want grams on the bottom so that they do cancel. It gives me 1604 grams per mole of CH4. Grams are going to cancel. We're essentially dividing, obviously, here by our molar mass, and that will get us approximately 3.468 moles of CH4. I would go to 4 sig figs based off of the original number there, as this would be an exact number. In this case, we actually then need to use sort of Avogadro's number to continue on. So we'll continue on here with our number. And once again, here we have moles. So moles need to go on the bottom. Avogadro's number needs to go up on top. We also want to make sure that we do use our exponent button here. And this would be molecules for Avogadro's number, as we're doing with CH4, which is a molecule. The moles here will cancel. We're going to multiply 6.022 exponent 23. Going to yield us something like 2.088 times 10 to the 24 molecules. Any questions on any part of that calculation there? So molar mass, grams, moles, gram conversion factor. Again, we get it from the periodic table, and obviously moles to atoms or molecules and back and forth there. Avogadro's number that we use. Any questions on that there? Okay, let's try a couple more here. That is a mole of everything. We sort of talked about the conversion there between them. All right. All right, so why don't you give this go? Number of grams there are in 15.7 moles of iron. Iron is 5585 on the periodic table. Okay, so when we look at this, we want to calculate the number of grams of iron in 15.7 moles of iron. In this case, we do not need to use Avogadro's number as there's no mention of molecules, atoms, or anything like that. So it really is moles and grams conversion. So that is the molar mass from the periodic table, which is basically 55.85 grams per mole. So here we would take our 15.7 moles. In this particular case, we do want moles on the bottom, and we do want grams up there up on top. This way, when we do the calculation here, our moles will cancel. That will give us 15.7 times 55.85. Going to give us about, we'll call it 877 grams of iron in this particular case. Here, once again, to 3 sig figs based off of our original number, as our molar mass will be more of a exact number. This one, how many atoms are there in 0.551 grams of potassium? Okay, let's take a look. So in this case, we are looking for atoms. So that's a key word to tell us that we do need to use Avogadro's number in this case. We are starting with grams though, so we do need to get it to moles because that's what Avogadro's number uses. So we do also need to go to moles here, and that would be our molar mass that we need to do that from. So that's where we'll start. In this case, it's just potassium, so we could just simply take it from the periodic table. And once again, that would be that there are 39.1 grams per mole. It's the molar mass of potassium. Starting with our grams here, doing a little dimensional analysis. We're going to throw the grams on the bottom, which means the 3910 goes with it by moles. Basically dividing by the molar mass here, we'll get rid of it, and we will get 0.551 divided by 39.10 gives us 0.01409 moles of potassium. Once again, that is close to what we're looking for, but we do need to get to atoms. So continuing on here, and by the way, you could just continue on with the calculation in this case without getting a number. We will use Avogadro's number here, 6.022 times 10 to 23 up on top, which would be atoms per mole. Moles here should cancel. Once again, we want to make sure we do use our exponent button. So 6.022 exponent 23. Going to get us an 8.49 times 10 to the 21 atoms of potassium. That is a lot of potassium, guys, floating around. Any questions on that calculation? And once again, like I said, you could do it all in one big calculation. You don't have to get the answer in between here if you want. If you do get the answer in between, which is perfectly fine, just maybe try not to round too much here so you don't move yourself too far away from the right answer along the way. Any questions on that there? All right, let's take a look at a couple more here, maybe. Let's see what we got. All right, so why don't you try these two here, helium and zinc. Helium is 4.003 and zinc 6539. Okay, so in the first one, we're looking for moles. We're starting with grams. So really all we need is the molar mass here, no Avogadro's number. So this would be 5.46 grams of helium. Using our molar mass from the periodic table, we're going to go grams on the bottom. So it's going to be 4.003 grams per mole. Grams will cancel, and we're going to divide basically by it. So 5.46 divided by 4.003 gets us a 1.36 moles of helium here. Looking at our second one, we're looking for grams, and we are starting with moles. So once again, molar mass is all we need from the periodic table, 0.256 moles. Once again, that is moles, not molecules. We are going to actually put the grams up on top. So our 6539 grams will go up on top. Our 1 mole will go on the bottom. They will cancel. And that gets us 0.256 times 65.39. And that's going to give us a 16.7 grams of zinc in this case. Any question on either of those calculations? Yeah. All right, so let's see what we got. I think let's get that one. All right, let's take a look at this one here together. So how many hydrogen atoms are there in 72.6 grams of C3H8O? In this case, we're interested in atoms, so definitely Avogadro's numbers involved. We have grams, which means molar mass should also be involved because we need to get the moles. The difference, though, here is we're actually looking for just hydrogen. We're not looking for everybody that is here. So in certain problems, you may be asked about a particular element that's there and not the entire thing. And we could actually do that by actually using the actual formula as a conversion factor. So when we look at something like C3H8 and O, all the numbers are on the bottom, and obviously no number, which represents 1 here. These all can be referred to basically as the moles of each of those guys that are present. So from the actual sort of formula, we could come up with some conversion factors that allows us to go from the entire thing, in this case, the C3H8O, to really just the hydrogen part. So for example, if we wanted to know in 1 mole of the entire thing, there would be just 3 moles of carbon, and that would come from the 3 that we see on the bottom here. We could say in 1 mole of the entire thing, there would be 8 moles of hydrogen, which would come from here. And we could even do it for oxygen as well. In 1 mole of the entire thing, there would be 1 mole of oxygen. So using those subscripts in the formula as the moles of each of them, we could actually come up with sort of a mole to mole relationship. And that allows us, again, to conveniently go from the entire thing to each of the elements that are present. Now, in order to do that, it is obviously a mole to mole relationship. We do need to get these grams into moles to do that. So that would really be the first thing that we would want to do. We would need the molar mass to do that part. So the molar mass of this guy would be 3 times 12.01 for the carbon, plus 8 times 1.008 for the hydrogen. I'll go underneath it, plus 16 there for the oxygen. Once again, all those numbers coming from the periodic table gives us 3 times 12.01 plus 8 times 1.008. Plus a 16. Looks like a 6009 is the molar mass here of this guy, grams per mole. So now that we have the molar mass of the entire thing, we could use that in the grams of the entire thing here to start our calculation. So 72.5 grams of the entire thing. Using our molar mass here, we're going to do the grams on the bottom, 6009 grams per mole. At this point, we have gotten rid of grams of the entire thing, and we're left with moles of the entire thing. Once again, we're not looking for the entire thing, but just the hydrogen atom. So that is where we could use this relationship here now to take us from the entire thing to just the hydrogen. So I'm just going to do that all in one calculation here. So On top is moles of C3H8O. On the bottom should go the same, so they cancel. Up on top would go our 8 moles of hydrogen. So that step there that we got from the actual formula is going to allow us to go from that whole thing now to just hydrogen, which is what we're looking for. If we were to stop right at this point, we would be in units of moles of hydrogen, which once again is close to what we want, but we do want atoms of hydrogen, which means we do need to use Avogadro's number here to do that. So we do have one more step in this process here to go from moles to atoms, which would involve Avogadro's number. So doing that in the same calculation here, a mole of hydrogen would be 6.022 times 10 to the 23 atoms of hydrogen. The moles would cancel. So we're going to multiply everything that's on top there. So 72.5 times 8 times 6.022 to the 23. We're going to divide by what's on the bottom, divided by 6009 basically. And that is going to get us 5.81 times 10 to the 24 atoms of hydrogen in this particular case. Any questions on any part of that calculation? So once again, you can be asked about a specific element and within a sort of formula. You could actually use the formula as a conversion factor to allow you to go from the whole thing to each individual component. You obviously could do a similar calculation for carbon, oxygen along the way as well. Any questions on that there? All right. Any questions on converting grams to moles, moles to grams, Avogadro's number? Like I said before, molar mass, grams to moles, moles to grams, definitely something we do a lot in a lot of different calculations. Any questions? Okay. All right, so we'll kind of skip these since we kind of did some of these. All right, then let's talk about percent composition by mass, which we sort of did a little bit with the lab that we did. Percent composition by mass really is the mass of each individual element divided by the molar mass of the compound times 100. Basically gives you the percentage by mass of each of those. Obviously, the higher percentage means that there's most of the mass is made up of that particular element. So if we wanted the percent by mass of C2H6O, the first thing that we would want to do is calculate the molar mass, which is there on the bottom. And again, that does come from the periodic table, basically how many grams per mole there are. To figure out the percentage of each of the elements here, the percent carbon would be the mass of the 2 carbons in this case. So 2 times 12.01 grams per mole, divided by the molar mass of the entire thing here, 4607 grams per mole times 100%. And that is going to get us 2 times 12.01 divided by 4607 times it by 100, going to yield us about 52% or so, 52.14% carbon in this case. We could do the same thing for hydrogen. In this case, the percentage of hydrogen would be 6 times the molar mass of hydrogen from the periodic table, divided by our 4607, which is the molar mass of the entire compound, times it by 100%. And we will end up with about 13, we'll call it, hydrogen. And obviously here we could do it for our last element, which would be the percentage of oxygen. And that would be, since there's just one in that compound, 16 grams divided by 4607 grams per mole times 100%. And that's going to get us our final percentage here of about 34.73% oxygen in this case. Any questions on any of that calculation there? When I add up all my percentages, they should equal 100%-ish, ballpark of 100%. Obviously, they do, if you add up all these percentages to give us 100%. They don't give you 100%, then probably something went wrong, but it should be about 100%, maybe a little less, maybe a little bit more with rounding, but should be definitely in that ballpark. Also, as we might have talked before, after we got these two percentages, we also could have just subtracted 100 from the other two, and that would give you obviously the missing percentage that would be left over there for oxygen. So you could have done that as well. Any question on percent composition by mass? Kind of similar to what we did with the percentage of water in that particular experiment we did, I think, last week or the previous week. All right. So percent composition by mass is used a lot, kind of like what we did in those experiments, to help us calculate one of two things, which is the empirical formula or the molecular formula. And a reminder that the empirical formula is the simplest whole number ratio of what is present. And that is different than the molecular formula. Molecular formula tells us exactly what is present. So for example, if we had something like hydrogen peroxide, which is the molecular formula, that is again 2 hydrogens for 2 oxygens. That is basically the same thing as saying 1 hydrogen for 1 oxygen, which would give us an empirical formula of HO. We had C4H12. That is basically 4 carbons for every 12 hydrogens. That's the same as 1 carbon for every 3 hydrogens, basically. And we could have an empirical formula, which would be CH3 in this case. So the empirical formula is the simplest set, basically, of whole number ratio of what is present in the molecule. Molecular formula does tell you exactly what's there. Sometimes the molecular formula and the empirical formula are the same. So something like water, that is 2 hydrogens for every 1 oxygen. You really can't go any lower than that and still have a whole number. So water would be both the molecular formula and the empirical formula. All ionic compounds are always empirical formulas because, frankly, that's how we put them together, right? We put them together in the simplest way to get to 0. And that means that we will end up with really like an empirical formula for all ionic compounds. So they're basically all kind of empirical formulas. Any questions on that there? Now, clearly we could do an experiment like we did last week, where simply, you measure something like we did. We started with so much silver. At the end, we put on some chloride. And by doing the differences in the mass, we could figure out the empirical formula. So let us talk about sort of the steps to calculate the empirical formula. First off, to calculate the empirical formula, you want to take any percentages basically and convert them to grams. So a lot of times in empirical formula type problems, you're given the percent composition by mass. So a lot of times you could assume that you have 100 grams of something. That means, for example, if you have 79% carbon, you would have 79 grams of carbon, right? If you had 30% oxygen, you would have 30 grams of oxygen. So by assuming 100 grams, it keeps everybody the same numbers and makes it really easy. Once you do that, and once again, you want to convert your grams to moles as the second step, and you want to use the molar mass to do that. So you want to take each of the elements, periodic table, convert everybody to moles. The third step is to divide by the smallest number of moles. So you're going to take everybody and divide by the smallest number of moles. So for example, if we had 2 moles of A and we had 4 moles of B, in this case, we would divide everybody by 2 moles. Gives us A2, gives us A1. And if you do that step and you do hit whole numbers, or very, very close to whole numbers, like super close to whole numbers, that would give you your empirical formula. In my example here, that would be my empirical formula at that point. Now, a lot of times there are certain times when you do the dividing part, you may not hit whole numbers. So for example, once again, if you had, say, 2 moles of A, but 5 moles of B, when we divide everybody here by 2 moles, we do get 1, but now when we divide our 5 by 2, we get 2.5 in this case. And this would give us an empirical form of A, B, 2.5. You cannot have basically a decimal. You got to have a whole number for an empirical formula. And 2.5 is too far away to round in a textbook problem. Now, in a lab problem like we did the other day, you could round to the nearest whole number, but typically in textbook type problems, you don't really round if it's too far away. So in a situation like this, what we need to do is figure out a factor to multiply the 2.5 by to get us to a whole number. So if you took 2.5 times 1, bless you, is 2.5. Take 2.5 times 2, that is 5. So we would want to multiply that formula by a factor of 2. And it's not just the 2.5, but we need to multiply everybody by that factor of 2. So we would take this entire thing basically and multiply everybody by 2. And that would give us the proper empirical form of A2B5, which is obviously whole numbers. So in textbook problems, for the most part, you do not round unless it's really, really close, like, 0.98 or something like that, 0.99. Maybe it goes over a little bit, like 0.01, 0.03, something like that. But typically speaking, if you end up when you're dividing with a number that's like 0.5, 0.33, something like that, maybe 0.25 or something of that nature, those are sort of too far away to round. So you do need to go through and figure out a factor to multiply everybody by to get to a whole number. Any questions on that there? Okay, so let's take a look at one here. There we go. All right, so we have this one here, which is determine the empirical formula with the following percent composition by mass. Potassium is 24.75, Mn is 34.77, and oxygen is 40.51. So let's take a look at this one together. So here we do want to quickly take a look at our percentages, and we do want to make sure that it does add up to 100%, and it does add up to about 100%. Again, if you added that all together and you did not have 100%, something is missing. So you got to figure out maybe what percentage is missing or something like that. In this case, we could assume 100 grams. And once again, by assuming 100 grams in this case, it keeps everybody the same. So we would have 24.75 grams of potassium. We would have 34.77 grams of Mn, and we would have 40.51 grams of oxygen. At this point, the next thing that we want to do is take all those grams, use the periodic table, and convert them into moles. So we would look up our potassium and divide by 3910. We would look up our Mn, which is, looks like 54 something, 54.94, looks like a winner. 54.94 grams per mole. And we would do it for our oxygen, which would be 16 grams per mole of oxygen. So dividing each of these guys by the molar mass from the periodic table, 24.75 divided by 3910 gets us 0.63299 moles of potassium. 34.77 divided by 54.94 gets us 0.6329 moles of Mn, and 40.51 divided by 16 gets us a 2.53, and we'll call it 2 moles of oxygen. Any questions so far? So percentages to grams, grams to moles. We want to look at all of our numbers. In this case, we want to divide by the smallest. They're very close, so we'll go with either one of these are pretty much the same-ish. So we'll divide by 0.63299. Took an extra digit on the top one, so we'll just go with that. 0.63299. In this case, when we do that, that is going to give us for potassium 1, that's going to give us for Mn1, and obviously here gets us about a 4 for our oxygen. We did hit whole numbers on all of those. That means that our empirical formula here would be KMnO4, potassium permanganate in this case. Yeah. Any question on any of those steps there? All right, why don't you try one then? Let's see here. Ask a question now. Actually, no, let's take a look at another one. I'll take a look at another way of doing empirical formulas actually. So another way that we can commonly do empirical formulas is through what is referred to as combustion analysis. And this is a common technique where we basically do a combustion reaction, which basically will take something that's organic, that has carbon, hydrogen, and oxygen, add a little oxygen to it, and we will get CO2 and water. And the combustion analysis is done by basically collecting CO2 and water. And from CO2 and water, what we can actually get from that is from the CO2, that will tell us basically how much carbon we started with, because all the carbon that would be produced there would have came from our original guy. From the water, that will tell us how much hydrogen came from it, as that also came from our original guy. The one thing that we cannot tell from the collection of carbon dioxide and water is how much oxygen came from it. And that is because part of a combustion reaction is adding oxygen, which means we have oxygen coming from this guy. We also have oxygen coming from our original guy. So some of the oxygen that gets into our CO2 and water is coming from the oxygen that's provided, obviously, by the environment, basically. So we can't directly figure out how much oxygen we started with by the CO2 and water, but we can combine them. And once we know how much carbon and hydrogen we have, we could get the mass of the oxygen by basically subtracting the carbon and the hydrogen from the mass of the compound. So in this case, you'll know the mass of the compound, which basically is carbon, hydrogen, and oxygen. From how much CO2, you'll know how much carbon there was. From the H2O, you'll know how much hydrogen. Subtracting those values from the mass of the original compound will tell you how much oxygen actually came from the original compound. Once you do that part of it, then it becomes like a regular empirical formula problem. You then will convert those grams into moles, and you'll divide by the smallest and figure out the empirical formula for it. So let's take a look at how to do that in an example like this. So we put our ethanol, which is basically carbon, hydrogen, and oxygen. We heat it up. It goes through this reaction, going to do a combustion reaction. We're obviously supplying a little bit of O2 in there as well. Going to collect some water and going to collect some CO2. And that's going to allow us to figure out how much carbon and hydrogen there are. So that's what we're going to start with. We want to take our 22 grams of CO2 that was collected in this case. This is going to allow us to figure out how much carbon there is. So the first thing that we want to do is actually convert our grams into moles here by using the molar mass of CO2. So that is 12.01 plus 2 times 16 for the oxygens. Going to give us 4401 grams per mole. Taking that, which is 4401 grams per mole of CO2, that's going to convert our grams of CO2 into moles of CO2. We're not really interested in this case in the entire CO2. We're just interested in the carbon part of it. And from the equation, we could see that for every 1 mole of the entire thing, there is 1 mole of carbon. So we are going to want to do that little conversion like we did earlier. 1 mole of the entire thing of CO2 will give us 1 mole of carbon, and that would get us 22 divided by 4401. That means that there is 0.4999 moles of carbon. And if we want to know how many grams of carbon that is, we now could use the molar mass of carbon, which is 12.01 grams per mole. And that will get us about 6 grams, give or take. So that 6 grams of carbon comes from this guy right here. There's 11.5 grams of the sample, so about 6 grams of it is made up of carbon. We could do a similar calculation using the water. So we collected, in this case, 13.5 grams of water. We're going to convert water into moles by using the molar mass of water, which is, we calculated earlier, 18.02 grams per mole of water. Once again, from the periodic table, 2 times 1.008 plus 16 there for our oxygen. Once again, though, we are not interested in all of the water part. We're really just interested in the hydrogen part of it. And we see for 1 mole of water, there is 2 moles of hydrogen. So we're going to use that conversion factor to get us to just the hydrogen. 1 mole of water, 2 moles of hydrogen. So in this case here, 13.5 times 2 divided by 18.02 gets us about 1.4983 moles of hydrogen. We can use the molar mass of hydrogen to figure out how many grams that represents. And that would be 1.008 grams per mole for hydrogen from the periodic table. That's going to give us 1.510 grams of hydrogen. So out of that 11.5 grams, 1.5 grams of it is hydrogen, 6 grams of it is carbon. And we are missing our last element, which is oxygen in this case. So we do know that the 11.5 grams of ethanol is basically the carbon, the hydrogen, the oxygen. If I subtract my 6.004 grams of carbon and I subtract my 1.51 grams of hydrogen, that will tell me basically how much oxygen was there originally. And that is 11.5 minus 6.004 minus 1.510 tells me we have 3.986 grams of oxygen. So this is the combustion analysis part of this problem, which is basically doing the calculation like we talked about earlier to figure out basically how much oxygen is there and how much hydrogen and carbon from the CO2 and the water gives us our carbon, our hydrogen, subtracted and gives us our oxygen. Any question on any of those steps there? Now that we did this part of the problem, we can now turn our attention to the empirical formula part of the problem, because now we have the grams of the carbon, we also have the grams of the hydrogen, and now we have the grams of the oxygen, which is the 3 things that we need. So the next thing that we want to do is convert those grams into moles. Yeah. The good news is the way I did it, I actually have no sense to reinvent the wheel. I already know the moles of hydrogen and I know the moles of carbon because I got that answer along the way. So really the only other one we need to convert into moles is our oxygen. So I'm going to convert this guy into moles. and that would be 16 grams per mole of oxygen. And we'll go up here, and that will give us, we got here 0.249 moles of oxygen. So kind of have all of our moles already. We could look at this and divide by the smallest. So I'm just going to recopy it over to the next page there. So we have that. All right, so let's take a look here. So we got 0.4999 moles of carbon, 0.4999 moles of carbon, 14983. 3 moles of hydrogen and 0.249. All right, so now we have our moles. We're going to divide by the smallest, which obviously in this case is the oxygen, 0.249, 0.249, and 0.249. Like I left off a number there, but that'll be okay. We'll do a 1, I think, maybe on that. All right, 0.4999 divided by 0.2491 gets us about a 2 there. 1.4983, 0.2491 gives us about a 6.01, and this gives us about a 1. So in this case, this is obviously close enough to round, which gives us our empirical formula C2H6NO, which would be our ethanol type problem. So in a combustion analysis,